Okay, guys, welcome back to the Panlow Circuit Design course. We'll start from the point where we left in the previous class. Uh, can you see my screen?
Not yet.
Okay.
Yes, now we can see.
Yeah, so I think we saw the DC analysis and AC analysis, and also we saw the pole zero analysis. So we came to know that there is a zero causing an issue for stability, that I'm getting the phase margin of 20 degrees only, instead 60 degree. Okay. So I supposed to get 60-degree phase margin now. So that we have to fix it here, right? This is the point where we left, right? Or anything else?
Yes, we were here. We're discussing the pole zero, and just as you said, yes.
Right. So what was the register value that we have designed for this compensation?
I think it was 526 ohm.
Oh, 5. Okay. 526 ohm. Let me take one.
Well, let me recheck. It's just a.
No, no,
I remember it was somewhere around.
it is right. So I checked it. 526. Okay. So this is where we have to place that register here. Okay. Let me take it here. Just push it. Okay. Yeah. Now we are done with this. So what we are trying to do here is, so there is a zero because of this capacitor shorting between output of the first stage of the diff amp and to the output of the common source amplifier, that is second stage of the op-amp. Okay. So diff amp is the first stage and common source is the second stage. So combined together will form two-stage op-amp, right? So now due to this capacitor, compensation capacitor CC, it's creating a zero, which is causing the frequency response to be going bad. So bad in the sense I'm getting the phase margin of 20 degree, supposed to get phase margin of 60 degree. So how can I do that? So as we know, right? So if there is any zero, it has to be cancelled. I have to place a pole on top of a zero. Basically, the frequency at which the zero exists, at the same frequency, I have to put a pole. Similarly, if at all I want to cancel out the pole effect, so how can I do that? So at the same frequency as a pole, I have to place a zero at that frequency. So that's what I'm trying to do. So since this compensation capacitor CC is causing a zero in the frequency response, which is causing phase margin to be very, very less. So now what I'm doing is I'm placing a pole on top of the zero by placing a series resistor. So this resistance value is exactly equal to the whatever the zero creating, that is the zero is being created by the GM of this MOSFET along with this compensation capacitor, right? Similarly, so the total resistance offered by this resistor should be equals to the one by GM of this, so that the exact frequency will get cancelled out of both poles and zeros, which is causing by this compensation capacitor. And now I supposed to get the proper frequency response. Okay, let's try simulating this and we'll confirm our calculations. Okay, so in the meanwhile, did you guys try that ADXL is working fine or not? So it is how much now? 158 degree. So 180 minus 158 will be how much? It's a 42 degree, right? 40 or 22, man. It is 22 still. 180 minus 160 will be okay. Only 22 only still I'm getting. So what's the reason behind it? What could be the reason? It is 22 degree only still I'm getting. Okay. What's the problem? Is this calculation right? So 1 by 1.9 milli. So how much it will be? Okay. So now I got something like 45 degree. Okay. So I think there is a calculation mistake, guys. So what you're supposed to, the formula is Okay. Can you see my screen of this? OneNote you can see?
No.
No?
Virtual server.
Okay. Now you can see.
Yes.
Okay. So this is what I think we have measured something here while calculating where it went. Yeah, this resistance I have just taken y1 by gm6, but in actual schematic, right? If I go to the lab, no, lab I can't. In actual schematic, where is that? Yeah, why it is not loading? What happened, man? Ah. So in the actual lab, right? So this is a diode connector configuration. So once it becomes short, it's a diode, right? So this resistance will not be exactly seen at this particular point. It will be again, it's kind of Miller we have to use here. Miller, or you can say voltage divider. So the total resistance will be seen with respect to this diode configuration will be separated, one from the input side and one for the output side. So if you use that particular thing, so the total resistance, so in resistance here is nothing but it's a cap, right? The impedance offered by this gate capacitor. That's what the resistance we are talking about. So I have to compensate that with one more resistor. So if you take that capacitive impedance, right, the total impedance that will come at the input side will be equals to the load impedance times of the this total impedance divided by sum of these two combinations. That's what the capacitive nature, right? It's just ulta of your resistive nature, resistance. So that formula we have to use it here. You got it? So the formula just I have copied is this. The total resistance of the zero will be 1 by gm6 times cl plus cc divided by cc. So this is what the total resistance. So this much resistance I have to keep in series with the cc capacitor, that is compensation capacitor. So let me try to calculate it here. So can you guys let's just calculate. CL is 10 and cc is 3. Okay, 13 by 3 will be how much? 13 by 3 into 0.526. It is 2.3K, right? 2.27K, right?
So 13 by 3, right?
Yeah,
4.3.
into 1 by gm6.
Okay, okay.
Now let me run this with the newer value. So newer value I have put here is 5.26K. This is what we got, right? Sorry, so 2.26, right? Correct, CC? Is that right?
Yes.
Great. Now we will see this with the newer values. It is 1.47 only. So now I sorry, Oh, now I'm able to get the phase margin from 22° to 45°. Okay, but whatever I have designed is not for 45, but it should be 60° at least. So we know that how this phase margin will affect the transient response of our Opamp. So the lower the phase margin, the higher the settling time, and vice versa. Okay, so basically I want my Opamp in the transient domain or a time domain should be very fast. If at all, it should be very fast in the sense it should operate with a high frequency so that my time will become lesser. High frequency means your like unity gain bandwidth should be higher. And along with not only unity gain bandwidth, at a unity gain bandwidth, your phase margin should be at least 45 to 60°. So what I have assumed is 60°. So I have to get 60° phase margin. So for that, what is happening here is that 0 is causing. So that now we will see that whether the 0 still exists or not. So now previously it was 22°. Now it became 45° as a phase margin. Okay. Now let's look at the graph of this pole zero analysis, where
Hello.
yeah.
Sorry, the phase margin here is 180° minus 147.
Yeah, how much it is?
33.
Yeah, 33.
It's 180° minus the point that you have highlighted, that 147, right?
Yeah, correct. So that should be the phase margin. So how much it is? 45° or 33°?
33.
180 minus 147, man. Yeah. So this is 33°. Correct. Okay. So still there is a failing, right? So now we have to make it 60°. Now before that, we will analyze whether that 0 got cancelled out or not. If that is not cancelled, right, this still exists here. So let me go to that pole zero analysis and both poles and zeros, plot it. Oh man, so this is our problem. So I have cancelled out this 0, but there is one more 0 got introduced, which was not there before, right? This was there. Here only there was only 1 0, right? Correct, if I am not wrong. Is that right? Or this is wrong? Now we have cancelled out this 0, you can see, right? So it was 0, so I have placed pole at 153 megahertz and 0 is at 153 megahertz. So this 0 is been cancelled out, but so by introducing that pole, so unfortunately there is one more 0 is getting introduced here. What's the frequency of it? 153.28 megahertz. So how many poles are zeros are there at the same frequency? This is at 153.28. But how come there will be two different zeros? So that is here. No, it is pointing to still sim. So I think we have to put it here. But you can see this is at 110 megahertz. Okay, if you see the x-axis, that is the frequency. It's around 110 megahertz. But why this is not able to cancel that? So what I will do is, now I think this got cancelled out. Okay. Yeah. So now I don't think it will be having the frequency response problem. Let's see that. Mhm. It is still 151 degree. Again, it got reduced. Okay. — 144. 14 megahertz, there is one zero. So that zero will be how much it is here. So to 40. One 137.6 means, let's say 137 in the sense it's 43 degree. It is 43 degree. Let's see the log plot where it will show poles and zeros. So there is a pole at 7.8K. That is there is a pole at 15.3 megahertz. Okay, and there is a zero at 38 megahertz. So I have to cancel out this zero. This is a dangerous for us. 38 megahertz in the sense 38 and 152. So 38 I have to cancel that out. So in order to have 38 megahertz pole, hey, come on, man. So how come we become 1 picofarad? Huh? Guys? Hello?
Yes, sir.
How it become 1 picofarad?
No idea.
Come on, man. That's why we are struggling here. So we did something, sir, here. So 2.26K. Okay. Correct, right? We have designed that for 3 picofarad, right? Not 1 picofarad as a compensation capacitor. Is that right? Yes, it is 3 picofarad. I don't know how it became, 1 point, so 1 picofarad there in the simulation. No, all result, no, that gain should not change. Gain will not change, by the way. Only this frequency response will change. That is phase margin. That pole location will get changed here. Let's see now, or where it went actually. Okay. See, now it's coming correct only, right?
65.
Yeah. So everything is there. Simply we are struggling, man. So I don't know why, how that value got changed. See, 75 degree dB gain. Okay. Something is wrong. So did we do any mistake in while entering the values? That we don't know. Anyways, so we are just putting the exact numbers of what we calculated. We are able to get it. Okay. Okay. So 180 minus 113 is a phase margin, and zero crossover frequency is 13.6 megahertz. We have designed it for 10 megahertz, right? So that is also in good range. And we have designed for like 2000 gain, right? So what is the 2000 gain? 20 log of 2000 is how much?
66.
66 dB. Yes. So we are getting 75. So 75 means how much it will be in terms of magnitude? 75 dB means, is it 5000? Yeah, we are getting more than 5000 gain. Okay.
5623.
Right, right. So any questions, guys? So now you are able to properly design and simulate and see exactly the same number we are matching in the lab as well. Not exactly, it's more actually. So which is very good for us. So what we're intending, by the way, this is nominal simulation, definitely it will match. So once you do the cross corner, right, there you may violate something, so you need to fix that. So how I just now fixed it. All right. So what we did, so just we summarize what we did here. So this is what Opamp we have designed, in which this is how it looks like, the structure wise. All right. There is a diff amp and followed by a common source amplifier. Combined, these two configuration will give me a two-stage Opamp design, right? So we know that there is a frequency compensation needed to place the poles and zeros at the proper places on S domain, that is frequency domain. So for that, we need this compensation capacitor. Okay. So we came to know that is introducing the compensation capacitor is giving me extra zero, which is causing stability issue. Essentially, it is introducing a 0 in my frequency response, which is violating the required phase margin. So how can I fix that? So we have fixed equivalent resistance in series with the compensation capacitor CC to place a 0 at the same frequency as of, sorry, to place a pole at the same frequency of 0, which is creating a problem in the frequency response. Okay, to placing that particular pole, right? So what it will do, it will just cancels out the 0 effect and gives me the proper frequency response, the smoother one. Okay, so how to calculate this resistance value? So this CC we already know, we have calculated from the phase margin, but the total resistance that I have to keep in series with the CC should be basically these two products should be equals to the 0 frequency, that is 1 by 2 pi R into compensation capacitor CC. So what is that R? R will be here 1 by GM of this MOSFET. Okay, this also has the load effect, that's CL. So that formula just now we saw, that is this resistance that we have to keep here is equals to 1 by GM6 of this, that is this is common source amplifier input MOSFET times total load capacitor plus CC divided by CC. Since it's a capacitor, right, it will be a reciprocal of your normal resistance equations. Okay, now so if I place the same resistance value which I got in the calculation, so now I'm able to see that particular 0 got cancelled in the frequency response, so which I'm getting proper phase margin as well. So now let's see this pole 0 plots and where and all zeros I'm getting. So it should not be at the lower frequencies. The zeros at the higher frequencies are fine for me. Okay, so at least like some 50 megahertz at least. Okay, yeah, so I think there are two dominating zeros which is causing issues inside my frequency response. This 0 will be cancelled out by this pole effect. So though they look apart here in the graph, but if you see the frequency, they are very close by. You can see that in your simulations also. This frequency of this pole and this 0 will be very close by, around like maybe hardly here and there 1-2 megahertz difference. So that's fine. Similarly, this particular 0 effect is cancelled by this particular pole. Okay, so now what we are doing here essentially that we are cancelling out the zeros effect which is causing issue in the frequency response, that is lower frequencies. Now we are able to get the proper smooth curve, so that you can see in the left side. And also if you see the red gain I'm getting is 75.5 dB, which is like more than 5600 magnitude, and I'm able to get 66 degree as a phase margin, which I have designed actually for 60 degree. So this is a typical simulation. So we are good and about the ranges that we have designed. So now you guys have to see in the across corner simulation whether this is violating or not. Okay. Any questions, guys, here?
Hello.
Yeah.
I have just a small question. Like here we calculated for like open loop phase margin and gain.
Yes.
In closed loop, it will decrease, right?
Definitely in the closed loop, these will not be even valid.
So generally for like any amplifier design, whether it's a single stage or two stage, the phase margin that we take for as a design parameter, that is for open loop or closed loop, or they are specified differently?
As far as I
Like
know,
this.
right, we generally define it for open loop, not for the closed loop. So closed loop is a user dependent, right? So whether the user want in the unity gain closed loop or he has some closed loop gain he wants, that is left to him. We don't know
Okay.
what exactly the requirement that user has. He can use as a unity gain also, or he can use as a closed loop gain of 10, 12, 15. We don't know that. Depending on the feedback register or capacitor he puts, that value will vary. But whenever the designer will design any op-amp, it depends on everything will be open loop. So these parameter, whatever we are talking about, gain, phase margin, common mode rejection ratio, CMRR, that is, so common mode gain, differential gain, PSRR, everything is open loop. Nothing is closed loop here.
Okay. Okay.
Yeah.
Also, one more small query. I was thinking, like, we calculated this resistance to cancel out the poles and get the required phase margin, and we reached up to 65. And suppose if we increase this resistance furthermore, I think we can get more better phase margin. Is that true?
Yes, yes. That time,
Yes.
that case, you have to compromise on your unity gain bandwidth. Which is
Okay, so
essentially the
unity gain
speed.
band will,
Yeah,
okay, that will decrease.
definitely.
Okay,
You know
yes.
why it
Okay,
will
okay.
decrease? You know, right?
Because
Yeah, this
because
will
we are
shift
shifting.
to, yeah, shifting
Okay.
towards lower frequency. This will become sharpen
Yes.
here at this point itself. So this
Yes. Okay.
crossing frequency will be decreased.
Okay. Thank you.
No worries. Yeah. Any other questions, guys? Good question, Karthik, by the way. Yeah. Naimish joined. Wow. It's surprising, sir. So Karthik, by the way, where do you stay? In US itself or it's different time zone? PST.
I'm in Ireland, Europe time zone.
Okay, Europe. It's hardly like 3-4 hours difference. 4 hours?
5.5 hours.
Yeah. Okay. So it's difficult for Naimesh to, sorry, Naimesh. Only you are the person who is having more time lag.
It's okay. I can do that. So
Yeah.
I'm glad to like be part of this. That's not a big thing. Yeah.
Thank
Yeah.
you. Thank you. So hope you
Sure.
got this, we missed something, Naimesh, in the schematic itself. So we struggled for half an hour. What was the
Yeah.
mistake? You were there?
No, I wasn't actually. I had some. Yeah, I woke up late actually.
No
I had some
problem.
things going on. Yeah.
So anyway, we will recap it now. Okay. So any other questions, guys, before I go for recap? Okay. So what Naimesh we did wrong was, so before I think 2-3 we just joined. Let me recap it again. So anyway, we just now like 5 minutes back I did it. So anyway, so we have two stages in this two-stage op-amp, right? So one is differential amplifier, one more is common source. Okay, we have connected these two in the cascade form. That is, output of the diff amp will go to the input of the common source, and output of the common source will be the actual output of your op-amp. That is two-stage op-amp, right? So,
Right.
so when we clubbed these two, that is in series, so we came to know that, and we definitely come to know that there is some compensation needed for the stability. That's why we took this compensation capacitors AC here. So after keeping this, we realized that this guy is also creating a problem in my frequency response. So what is that? So that is, it's introducing a 0 in the frequency response, which is causing phase margin to be decreased. So that is also like a kind of undesired effect that I don't want to happen in my circuit, right? So
Yeah.
to avoid that, so what I have done, so we are very familiarized with it, right? So in the stability we have studied, so how to cancel out the zero effect, how to cancel out the pole effect. It is just ulta. If it is a zero is creating problem, just place a pole on top of zero. When I say on top of zero, it's a pole frequency and zero frequency should be same. Similarly, a pole is causing problem. If at all that is the case, then keep a zero on top of pole so that the on top of pole so that the pole effect will be cancelled out. That's what we are
Yes.
trying to do it here. Okay. So what we are doing here is, so this CC is introducing a zero because at one frequency this will become a short circuit. It's a capacitor behavior. Short
Correct.
circuit means like V out one will be
Feed
shorted to V out.
Yeah.
Yeah, that I don't want to happen.
Okay.
Yeah, so what I will do, I will place a pole at a frequency at which this capacitor is becoming short. How will I place a pole? So by introducing a resistor in series with this, so these two combinations will create a pole now.
Okay.
So these two combinations will create a pole at the frequency exactly same as the zero frequency. Okay.
Okay. Correct.
So what it will do, though it is shorting, so this resistance is helping me to cancel that shorting effect. So now the question comes here is how much resistance I should keep it here. That's a question. So we know that capacitive impedances will be reciprocal of resistance impedance that we generally calculate. For example, your impedance XC will be 1 by 2 pi f, right? But for the resistance, it's directly proportional.
Yeah.
Similarly, the total resistance that we keep here will be equals to. So let's say this resistor is not there. We have not yet placed the pole. This will be short for one frequency, right?
Correct.
So at that
Right.
point, it will be diode. You can see, right? If it is short,
Yeah.
it is just a
Correct.
diode, right?
Right.
So what's the impedance of the diode? It's just 1 by GM of this.
1 by GM. Right.
Right. Okay. So I want to place a pole at the point where when it gets shorted. So I have to take that particular impedance, that is 1 by GM of this MOSFET, and
Right.
also the combined effect of this compensation capacitor as well as this load capacitor. Because this resistance will be getting divided between these two branches actually. One is this input branch for this particular output stage is concerned, and one more is output branch, that is CL is connected here. So, okay, so the total resistance will be 1 by GM times of this into CC plus CL divided by CC is the total resistance that I have to keep it here. Okay.
Okay. Okay.
Yeah. So if I place that exact same resistance I have put, I did not change even values also. So I'm able to see the graph as well as the pole zero locations. You can see it here. Okay. Yeah. Now this is a graph where we are having phase margin as well as the gain. So you can see phase margin is coming as 114. I mean, basically calculating the phase margin 180 minus whatever
180
the total
yes.
phase shift we will get at the zero crossover frequency.
Right.
It is 114 degree. So 180 minus 114 will be how much? 66 degree, right?
Okay.
Yeah. So that is what we have designed it for 60 degrees. So we are getting 66 degree at the nominal. So definitely it will even qualify the Slew as well. Maybe 10-15% variation. That's fine. And if we take the gain, so we have designed it for 2000 magnitude. So I'm getting 75.5 dB, which is nothing but 5600 and above. So that's also good. So this particular Opamp is like as typically is concerned, it's very good Opamp, and we can use it for even higher frequencies like 10 megahertz, 12 megahertz, and it has very less error as well. Since the gain is higher, you will get very less error when you compare with any reference signal.
Okay.
And similarly, if you see the pole zero graph, so we are worried for the poles and zeros which are near to the zero frequency, that is DC. So this is the zero frequency. Okay, this particular line, you can see that zero is here.
Yes.
We have to worry more about zero and left of the zero till some few tens of megahertz. Okay.
Right. Right. Yeah.
So what is that few tens of megahertz? So how will I get to know, right? So that's the most important question that we have to consider. So what is that few tens of megahertz that we have to consider the number of poles and zeros, right?
Yes.
Yeah. So generally what will happen is, so you know that unity gain bandwidth, we have designed it here. It's a 10 megahertz. So we are getting around like 12 megahertz something. Okay. That's fine.
Correct. Yes.
But the number of poles and zeros that are dominant to this particular spec is at least like 5 times you need to take. 5 times means 10 megahertz if I design. Okay. It will be 50 megahertz.
Okay.
Generally, it's a 5 to 10 range that we consider. It depends on designer to design. Okay. It depends on what is the different application it's going to. It depends on that. But general, very general, it's a crude way. Okay. So it's a 5 to 10 times of your unity gain bandwidth we have to take. Okay. So here I'm designed for 10 megahertz. So generally I will take 50 megahertz as a threshold for me to consider number of ports and zeros. So now let's say, so now till if I go to even 10 means like 100 megahertz, it will come somewhere here. Okay. So I have a 0 here, and just beside to that I have pole. So though we see it's separated so much here, but if you take absolute frequency of it, right, it will be very close by with the difference of around 1-2 megahertz or something, very less. Okay. So this 0 effect will be cancelled out by this particular pole. Similarly, this 0 will be cancelled out by this particular pole. Okay. Now you guys should be familiarized with these pole 0 and analyzing the poles and cancelling it out. Okay. Any questions, guys? Yeah, go ahead.
This 5 to 10 multiples of the unity gain bandwidth you chose, that's just a practice, which is, it's still far beyond the unity gain. So, I mean, it's phase wise and everything is out of the range, right? So why 5 times? 5? Actually, yes.
Oh, no, I didn't get your question. Yeah.
So you said like you choose, you consider the poles and zeros that are multiples of 5 times the unity gain.
Okay.
So you consider that, so those poles and zeros are out of range, right? Like more or less.
Yeah.
So still we consider them to be a little concern as far as like a design issues.
Yeah.
Yeah, I see.
Yeah, you know what, like, yeah, okay. It's a good question, by the way. So you are able to see my OneNote?
Not yet, no.
Okay. Okay, let me, I think I don't have pen here. So do I have pen? No, okay. Okay, so I'll explain it here itself. Okay. Copy to, okay, what happened now? Copy to new window. Okay, yeah. So we know that, right? So there is around somewhere here, there is a pole. So if you see the exact number, it is somewhere around 7.3 kilohertz or something. So I can see that in the log as well, the pole location. The dominating pole is at yeah, it's a 2.6 kilohertz. Let's say 2.7 kilohertz. This is the first pole. The second pole is at 17.9 kilohertz. So 17.9 megahertz. Okay. And third is at 153 megahertz. Similarly, it goes on. And then the first dominating zero is at how much? It's at 36 megahertz. 36.9. Okay. Okay. So now you ask like, so how why we are taking like 5 to 10, even though it's beyond our poles and zeros that we consider. It's beyond our sorry, unity gain bandwidth, right? Yeah. So what will happen is, come here. So 2.6 means somewhere here it is a pole. Where is that? 2 point, yeah. So pole is actually here, right? If you see the x-axis, it will show the frequency. Somewhere here there is a pole. You can see, right, that effect is started already from this point itself.
Yes.
No, what theoretically we shall tell at exactly pole location, it should start 20 dB per decaying, right?
Good.
So you can see there is already decaying started at this point itself. somewhere around 0.5 megahertz itself.
Correct.
Sorry, 0.5 kilohertz, not 0.5 megahertz.
Yeah.
Yeah, if you see that, right? So the actual theoretical value, if I tell, the effect of the pole or a zero will start 1/10 of the frequency before itself. For example, let's say pole location is at 1 kilohertz. Okay, it effect starts at 100 hertz itself, the initial effect, and the exact pole effect will be at the exact location, that is
Yeah.
at 1 kilohertz, if I take example, and the effect still remains same, 10 times more
10
frequency as of
times.
this. Yeah, it's a
Good.
1/10 or 10th, so that's the range.
Yeah. Mhm.
Okay, that's why we generally take 5 to 10 range as
Okay. Okay. Okay.
the same holds good for zero as well,
Right. Right.
that effect.
Correct.
Okay,
Right. Okay. Thank you.
no problem. Any questions? Okay. Okay. No questions. We'll move on. Okay, guys. So now I have one assessment question for you guys. It's very simple. What you have to do is just you have to calculate phase margin and gain margin. Okay. How you should calculate? Just now I calculated phase margin, right? 180 minus this particular phase will be my total phase margin. Similarly, we have to write the expression to calculate it. Simple. How to write expressions? So you already know. I'll give hint as well here. Use the cross function. So what cross function does is it will give the frequency at which it crosses the gain of 0 dB. Okay. So that particular frequency it will give. Okay. Same thing. So that will be unity gain bandwidth as well. The frequency at which it crosses the 0 dB is unity gain bandwidth. Use the cross function for that. And for the phase margin, same cross function and 180 minus this particular phase at which this gain unity gain bandwidth is exist. So that will be your phase margin. Similarly, gain margin will be how much? When this particular phase becomes 180 degree. It is 131 here still. If you simulate for the longer duration, right? I have just simulated for how much? It's 100 megahertz. If you simulate for around 1 gigahertz or something, you will get full 180 degree as well. So with that, you can calculate gain margin. So that is not needed here. So you can calculate only unity gain bandwidth, phase margin. That's enough. Okay. Anyway, we have saw here in the graph, but it's better if you get something like expressions here and direct values we can see it here. Okay. Any questions, guys? Okay. So what are things we have done till now? First thing, we have done the DC analysis where we have placed all the MOSFETs into saturation region and we made sure that it's not violating any rule, that is saturation rule. Okay. The second thing what we have done is we did AC analysis as well to calculate the gain, and we saw that there is a problem with the phase margin. Okay. And we have fixed that with placing a resistance in series with the compensation capacitor. Essentially it does is it places a pole on top of 0 to cancel out its effect. Now these two are done. So same thing, we have saw the number of poles and number of zeros in my complete circuit within the range of frequency that I have given. So that also we saw, and we are also able to see how it actually cancels out the pole and zeros in the pole zero analysis as well by placing zero on top of pole or pole on top of zero, whatever the needed one. Okay. Now let's look at some other simulations that what are other simulations pending, sir, here? The AC done, DC is also done. Transient we will do it. Okay. Transient we will do, and stability we have to do. Yeah, stability and slew rate we have to do. What else? Okay, we will do all this stuff. Okay, now I will close this off. By the way, you guys started working on your project, or anything is blocking for you guys to start on that?
Like the inductor that is in analog library, that they have Q values, one inductor there where we can set the Q values of that inductor, and like and then there is one inductor where that is normal simple inductor, just has inductor values only. So should I take the Q value one, right, for that schematic like VCO?
Yeah, so but by the way, yeah, that is right, you need to have the Q valued one, but you can also calculate Q value by using inductor value itself, right?
Yeah, then the true. Okay, and then okay. Yes.
Yeah, as of now you can go for Q1, but actually you can calculate the Q value by using inductance itself.
Yes, yes.
Yeah. Okay, now we will start with others. Okay, now we will calculate the slew rate of it. Okay, for the slew rate, I have to have transient analysis to be done on this Opamp. What I will do is I'll simulate for 10 microseconds. Okay, Now what I will do is frequency, let's say 1 kilohertz I'm using, and amplitude is 1 millivolt. Okay, let's do the transient analysis on this and we will see the graphs. Are why, man, it is not coming? First thing, why this input is keep on rising? What is this?
So we doing transient analysis, but in the voltage source, you also have the AC. Right? Is it, do we have to?
I don't think it will affect. Let's try that also. It's a valid, but it's amplitude is this outside. Okay, this is fine. Hey, come on, man. This is correct only. So, see, 1 kilohertz is how much, man? It's 1 millisecond, right?
Your simulation time is
Yeah. What is this, man? Huh? It's working fine, I guess. Hmm? Yeah. Now I have to increase even frequency also. Let's see that. Why? It's a unity gain, right? Okay. We'll increase the frequency to 1 megahertz. We'll get at least 10 cycles. Okay, it's always better to simulate any circuit for at least 10 cycles. So sometimes it will go up or down to make it a proper, simulation results. You have to simulate for 10 cycles at least. Oh, what is this? Output is this? It is this. So we will see the peak to peak value. So this is a transient analysis, okay, for unity gain amplifier. The input is how much? It's 1.98 milliwatt. It's a 2 milliwatt, okay. 1 milliwatt upper side and 1 milliwatt lower side. So even output is also 1.97. It's exactly matching, okay. Now it is a unity gain buffer, which means that buffer. It's a basically buffer, which means that output is exactly equals to the input. Now I have given a swing of 1 milliwatt peak to peak at the input, and same thing I'm getting at the output. But you can see input common mode and output common mode range are different here. That's why your green and pink are not exactly in the same line or same phase. It is just shifted up. Okay. Any questions, guys? This is to illustrate your transient analysis for unity gain bandwidth. Sorry, unity gain buffer.
We have feed offset here.
Yeah, it's not a kind of offset, you can say. Yeah, it's little offset also, but here it is common mode levels are different, right? Input and output common mode. See here, input common mode is decided by diff amp, okay, but output common mode is decided by this common source. So this has a wide range compared to this. That's why you will get some shifted version of your strings. You can see this output is shifted up, right? It has the wider swing, basically. It has wider headroom. It's more headroom and tail room as well. But whereas this for input, you don't have much headroom, and even tail room also it's not there much. So yeah.
So is a is a slew rate positive and negative? Like, is that why you see the output when the output is rising, it's closer to the input, whereas on the right side.
That's true. You are right. You can see now we will do the slew rate simulation also, right? There you can see slew rate positive will not be exactly equal to negative because of your P and N mismatch. So will not be we have not matched the W bells of both N and P exactly, right? Because we don't have like some dots like fractional number matching here. It should be only a round figure. That is one thing causing that. The second thing is your mu n and mu p will not be exactly matched here because of that mobility factor. Okay. The third thing will be your mismatch, definitely, which is not there here, but definitely after layout you will get that mismatch. All right, understood, Namish?
Yes, I did.
Okay.
Thank you.
No, we will go to the slew rate simulation. Okay. I'll use the same Opamp. Okay. Same Opamp with here instead of this, right? I have to give a pulse. Okay. What I will do is I'll make same thing to the pulse, V pulse. Zero to what is this? This what is yeah, that is fine. 0 to VDD. What's the frequency? It's a one microsecond. I want to do it. Rise time, let's say 100 picosecond, and fall time is also let's say 100 picosecond. Okay, this first I'm getting the input. Let's see how exactly the output behaves. Here we address two phenomena. So one is settling time, second one is slew rate. Okay. Okay. Yeah. So now we can see this is how our output is behaving. Okay. My input has raised here somewhere, and my output is like slowly raising and ramping, and it's going, it's coming stable after very some time. So this is what your settling time. Okay. So if you see that here, so 1% of your 2.5 volt is how much? 2.5 minus 0.99. 0.99, yeah. So 2.5 minus 2.5 into 99%, right? That is 0.99. Minus 0.02. 2.47. 2.475. So here the moment it rises here is somewhere this point. To 2 point. This is your settling time. How much is the dx? It's 194.6 nanosecond. Okay, so the settling time is the time. How much time does your Opamp take to settle your output within the some percentage of your final value? So here the final value is 2.5 volt that it's supposed to settle. With some percent means that generally people will take 1 to 2%, some people 5%. Okay, now I have taken here 5%, which is worst case. Okay, for the 5% of the variation, it is taking 194 nanosecond. Okay, this is the settling time of this Opamp typical value. Okay, any question here? How to find out the settling time? So what we have to do, you have to for generally finding out any settling time or something time related stuff, right? You need to take standard functions, input functions, for example, step function, ramp function, impulse. So these are standard functions, right? So this we have to take to find out your rise time, fall time, settling time, duty cycle. Okay. Got it, guys? Okay. So now we'll continue the same thing for this slew rate calculations as well. So now I will take this output from here. Oh, sorry. From here to here. Okay. Send this output to calculator. Okay. Now from the function menu, take derive. Okay. What is derive? It basically do the differentiation on top of your signal and just plot it. This is your slew rate. Okay. So positive side you are getting something like 10.5, negative side it is 8.7. Okay. If you combine and divide by 2, that will be your overall slew rate. Why there is glitches are coming here? Anything wrong in this waveform? Okay, okay. Yeah, it is ramp up and ramp down is causing that. Okay. But still that also should not, right? Anyways, so this is how we calculate the slew rate, where it went when. Yeah. So this is a positive slew rate. Okay. This is negative slew rate. Negative is 8.788, that is 8.8. Positive is 10.5. So 8.8 plus 10.5 by 2 is your total slew rate. So you can see positive side it is more slew rate, which means that it is faster responding. Negative side it's a lower slew rate, right? Which means that it is telling in the negative side for the negative basically the falling pulse, it is not much faster. Okay. Any questions? Again, you can do the same thing. You can write the expression to find out this positive and negative for 2 and take it average, so that you will get the final slew rate. Okay. Any questions, guys, overall? Okay, so now what else is pending? Slew rate is done. Transient is also done. Settling time is also done. Yeah, stability is pending, right? Any questions before we move to stability? How to find out the stability? Okay. Okay, no questions means we'll move for stability. So I have created no schematic for that stability. Let's simulate that here. Okay, so what is stability? Can anyone tell me what is stability? What are the criteria we generally consider before we tell this system stable or not? Okay, so when we say our system is stable, so means like for any step input, so output is going properly, in the sense for step input we are getting step output without much ringing in the input. So sorry, without much ringing at the initial stages. Just now we saw that we have given the step function at the input, and we also saw the step function at the output with the more ramp up and ramp down time. Okay, so we say uh, system is stable in the sense for the bounded input we should get the bounded output, BBO. Okay, so what is a bounded input? The input is the one which we call it as a bounded, is nothing but we should be able to measure it accurately without any error. So that is bounded, it's within our boundary. So I can tell you this signal is like that. Okay, this has this much period, this much amplitude, this much phase. All the characteristics of a signal should be able to identify. That we call it as a bounded. So for all that bounded input, I'm getting bounded output. If that is the case, then the system is stable. Else, it's not stable. Okay, let's see how to measure the stability. So for measuring the stability, so we have to take something called iProbe. So what is this iProbe? It's a symbol that will help me to break the loop. So basically, I want to break the loop. Okay. So there is a criteria for breaking the loop to measure the stability. So what we have to do is, so let's say there are n number of loops. So now I have given only one loop, right? So from your output, I have given to the negative terminal, which will act as a unity gain amplifier, basically buffer. So there is only one loop. Let's say there are multiple loops. So what I will do is I will place some resistor here, and I'll connect it here, and I'll connect one more here, and I'll place some capacitor here from output, and again I'll connect to the same input. Let's say I have multiple loops from output to the input, and also like from output to positive input also there is a one more loop. So let's say there are n number of loops. So I want to measure the stability. Okay, so the number of loop increases, your system will more prone to unstable, because there are more number of loops. So multiple poles are and zeros are playing on your response of your circuit, so that may go to unstable. We don't know, it's more prone. That's what I'm making the point here. Okay, so now what I have to do is, no matter what, there are any how many number of feedback loops. So what you have to do before you do the stability analysis, you have to make sure that you are breaking all of the loops. Okay, means how to break. So this is a circuit loop breaker, it's iProbe. So I have to place this iProbe in such a way that it is breaking all the loops. So can you just identify the one way which will help me to break all the loops? Let's say there is one more loop from here to here. Let me connect it. Okay. So let's say there is one more from here to here. Oh, sorry. Let's say one more is here like this. Okay, I have one more something from here to here, here to here. Okay, there are multiple loops basically. If I place same a capacitor here, okay, I'm placing multiple. Essentially, what my intention here is to make multiple poles. Sorry, multiple loops. which essentially have different in the poles and zeros. Okay, this is what my intention here. And you can say there is one more capacitor here. Okay, these are all different loops. Okay. Okay. Now let's say for this circuit I have 3 loops. So I have to break this circuit loop such a way that it should break all the loops. So where is the place if I to break the loop of this particular circuit to make to do the stability analysis? What is the point where I can put that circuit breaker? That is loop breaker.
Just at the output of
Output.
Output. Okay, I'll keep the output.
no, sir, not there. Just
Then
at the mouth of Opamp, just at V out.
okay. Here.
No, just
Here?
this one. Yes.
Okay. Great. This is a point where it is breaking the all the loops, right? So this also loop got break, this also and this also. This is how we should identify in any of the complex circuit to make the stability analysis. So now I have placed here at the immediate output of your op-amp so that it will break the all the loop. Okay. Definitely loop will start at the output point only, right? No matter what, whether it's going which input or where it's going, I don't mind. But it definitely should start at the output node itself. So if I break the output node, then it will break all the loops. Simple. Now let's do the stability analysis here. I think this is all not needed. So 1 node stability, this is all. Which one? So I just need VDC. Okay. Now I have broke the loops. Let me do the stability analysis. So how to do it? So if you go to this analysis menu, you can see something dot stb, stb analysis. Stability means stb. Okay. If you click on this, select frequency and sweep range. So let's say from 0 to 100 megahertz I put. Okay. And it's automatically to automate. Now here it's important. Probe instance. So means which instance you want to do the stability analysis on. So you have to probe that instance. Select, click on select. It will opens up this window and select this instance. If you select, it will come to the point where it is having that here. Yeah. Oh, it's not taking. Hey, come on, man. I think I have to change the design here. See, it is still issue that I have to make it stability. What is this, sir? Huh? You have to tell. Yeah, now it's pointing to the correct schematic. Now I can do it. Okay. Now I can go to stability. Start is 0, end is 100 megahertz. And select instance. Probe instance, not instance, man. Probe instance means this. This. I probe 0. Yeah, I probe 0 it came. Now after this, done. Okay. Click on this. Now that stability analysis is added to your analysis menu. Now you can click this simulation. Now the stability analysis is done. Okay. So let's plot the results of stability analysis. See, if you go to the print, there is some stability summary. Click on that. Yeah, it will give you the phase margin, how much you are qualifying, frequency, okay, at what frequency it is able to qualify the phase margin. So the phase margin it is considering. So we got theoretically in, sorry, in the not theoretically, in the what is that, graph around 66 67 degree, right? But exactly it is 73.6 degree. It's a phase margin. And what's the frequency? It is 7.4 megahertz. So you may wonder, it's a frequency of unity gain bandwidth. So but we actually saw around 14 megahertz, right? So that is differential unity gain bandwidth. This is a single-ended, because you can see in the Opamp we have only one loop. So other loop is like shorted. It's a feedback. So we have given the input to the only one. It's a single-ended. Input is like not differentiate, differential one. That's why you will get half the frequency here. Okay. So the phase margin is 73.6 degree, and bandwidth is, unity gain bandwidth is 7.5 megahertz. This is what the stability analysis. Basically, you are trying to find out phase margin and the corresponding frequency. If the phase margin is failing, then you have to fix your design. Any questions?
Hello.
Yeah.
Sorry, the unity gain buffer is a closed loop system, right?
Yeah.
So our phase margin has increased from open loop system to a closed loop system?
Could be. Yeah, because you are closing the loop. So the pole locations may vary. It will definitely vary, by the way. And because of that, your unity gain also will vary, and your phase margin will also vary.
Okay.
It's very simple, right? When you close input to the output, if you take just simple common source amplifier only, okay. Let's see, if I take common source, this is the common source amplifier. Consider only this part. Okay. If I short these two, okay, and without shorting these two, so you can see the total resistance at this point will vary, which means that pole location will be at different point. If I short, the pole location will be at different point, right? You're getting my point?
Yes, because I'm trying to correlate, like in the theory we studied, suppose if we in the network system, if we have a loop that is going back to the input, but here, because we have differential input, so I'm trying to correlate, because suppose the gain will also be divided by that loop feedback factor.
Yeah.
And in our case, loop feedback factor is 1, so our gain is 1. But again, in like I think for phase margin also we'll apply the same, like it should reduce by that factor, right? Or maybe because it's a unity feedback, so it's 1. I'm just trying to correlate if it's
no actually it's a unity feedback, right? How it is feedback factor is 1 here. So but the phase margin we are getting is like different than what we saw in the differential case, right? But you are telling it should scale by the same factor.
Like I'm trying to correlate.
No, it is not necessarily. Yeah. So with respect to phase margin, right? So
yes,
there will be some effect by the way, but not necessarily at the same factor is what I can think of. So when I don't remember exactly that network analysis concept with respect to the phase margin is concerned. Yeah, if you get, you can please let me know also.
okay, thanks.
Yeah. Any questions, guys? I think we almost done all the analysis, right? Anything pending, sir, here with respect to the two-stage Opamp and the analysis is concerned? Anyone can think of any simulations we left for this particular two-stage Opamp? Okay, I think we have done DC, AC, transient, stability, slew rate calculation, rise. Sorry, what is that? Sorry, what is settling time? And what are things we left? So I think these are the specs we considered for designing it, right? So if I can go back, gain we have calculated, gain bandwidth is done, slew rate is done, input common mode also like we have saw that, load capacitor, supply phase margin we saw. What else we saw? That's it, right? Slew rate also we saw. Yes, sir. We are pretty much done with the two-stage Opamp. Yeah. Any questions? If not, we'll move to the other topology. So I hope you guys are able to simulate this on your own and do the different design as well. Okay. If not, if you face any query or some error, please let me know. And you can just post in the group as well. So if someone is faced already and has the workaround or a known method to solve it, so he can just post it. He can reply to your query. Okay, now I'm assuming so you are able to simulate on your own. Okay, any questions? No questions means we'll proceed for the telescopic transconductance amplifier. Okay, guys. So can we take break or we can continue? No one need break?
Maybe 5 minutes break should be okay.
Yeah. So we'll take 10 minutes or not 5 minutes.
Okay. Thanks.
So we'll meet, it's 6:01 in my laptop. So we'll meet at 6:11. Okay. Thank you, guys. Okay, guys, we'll start. I can you can hear me, right? Hello. Can anyone tell me that whether I'm audible or not?
Yes, you're audible.
Okay, thanks. Abhi. Let's go to the other topic. Okay. Uh, the next one is like telescopic Opamp. Hmm. Okay, for that, this output stage will not be there. ನೀವು ಸ್ವಲ್ಪ ತಗೊಂಡು. ಇಲ್ಲಿ ಇಬ್ರು ಶೇರ್ ಮಾಡ್ತೀವಿ. Okay, only this part exit, and there will be like sorry, cascoding part also. Cascoding devices. Now this completes the circuit of it, and also we'll do the bias generation here. Okay. So 1, 2 will 18, 11, 23, and 19, 19. Okay. Okay. Now the W balance of all these MOSFET got changed to 90. Okay. You can check any at a time. You can replace that. Now for this 1 and 2 is how much? 18, and 3, 4 is 11. This should be 18. So 18 means this will be 6. 18. Between this and this should be 11. This 23. Okay. Now what we will do is we will generate bias for this VBN2 and VBP2. So how to generate? We already know it. Right? Just take this circuit and we will get it done. And let's say this is the bias circuit, initial stuff. I think this is enough, right? This is to generate the bias for N MOSFET, and this is for P MOSFET. Correct? Okay, this will have the length of around, let's say, 6. Okay, now these WBRs are fine. So only I need to think of this bias generation one. So this will have 10 and 12. So this is 12. And this will also have 10. This will also have 10. Then what else? These two will have how much? Okay, let's see now. This should be 23 and this should be 12 and this should be 11. So this should be 10 and same thing goes here as well. 6. Okay, I think this will not. I have to have one more branch here. No, it will not work. This is not needed. So this should be taken from here. So now okay, let's try with this bias, optimizer bias. Here we made so much, complex one. I mean, basically it consumes more current. So I just made two branch there to generate both the biases. Let's see. Let's try this topology. Okay. Now I hope everything is fine. symbol is created. Let's close this and open the symbol. So okay, so how much was the current? It's 100 micro, right? So phase 2.5. Okay. Okay. Now I can open the schematic here. Okay. Now we will see how much is the input common mode. So 1 volt, yes, so we are given. So this is also 1 volt. Great. So how much is the common mode we have taken here? 0.9 to 2.3. Great. So now all good to go. Just simulate. Telescopic design schematic. Okay. Oh my God, why? Is something wrong? So vision 2 perfect, man. Okay. Let's see the vision analysis. Wow, you can see gain is 77.7 dB. And you will see this frequency response also. Frequency response is how much, man? It is 90 degree, 94 degree. What is this? It's so awesome, huh? And gain bandwidth is 15 megahertz we are getting. That's cool. Okay. 77 means how much it will be? The gain in magnitude. 7079. Okay. It's very good. Any questions, guys, here? So this much faster this no faster means the better slew rate, sorry, phase mark is due to it's a single pole system, single one dominating pole system, that we have taken load capacitor of 10 picofarad, right? This is causing very high only one pole dominating at the lower frequency. That's why our phase margin is much better. Whereas in the two-stage Opamp, there are multiple dominating poles playing, because of which we were getting the lesser phase margin. Okay. Any questions, guys, here with respect to DC, with respect to his bias is concerned, at least, right? See, this is very optimal bias. So even today only I got this thought. So even for the previous batches, I did not follow this. There were again complex bias circuits I have followed. Okay. Here it is very simple, right? It's a wide swing current mirror. That configuration will come here. I have taken length equal to 6 times of your normal length, so you can see 6 times, and I have taken just exactly the half. How much? Half the. Sorry. So exactly half the current I have taken here. You can see, right? Because here it is 12. 12 so 23, so here I have to make half the current. So what is the half current? The W will be half months, here is 12, so 50 microamps will flow here. So same, I am just branching it out here. Okay. So you guys are hearing me, right? And I'm not see any I can't see and I can't hear any sound from you guys. You guys are clear about this biasing?
Yes.
Yeah, great. So now we are getting better AC and DC responses as well. DC is everything in saturation, and AC, like magnitude and phase, we are getting very better. Now you can do on your own and try to gather this gain equation and phase equation and put that in the expression itself, so that it will be easy to view the data. Okay. Any questions you have till now with respect to telescopic is concerned?
Hello.
Yes, sir.
Sorry, will it be possible if you can just one more time explain the biasing again?
Yeah, definitely, sir. No problem.
Thank you. Thank you.
You know what? This we have studied in the current mirror, right? Basically, this is a wide swing current mirror. So anyway, this transistor is already biased with respect to this node. Only I have to bias this particular these two MOSFETs. So how much?
Yes.
So what is the minimum voltage I want at this point? VDD minus 1 VDS and 1 VGS, right?
Okay.
So that the 1 VDS and 1 VGS should be dropped from the VDD.
Okay.
So how I should generate this? So basically, 1 VTS plus 2 overdrive should be dropped from the VDD. So how can I do that? So with this, I'm able to drop one VT and one overdrive, right? With their connected configuration.
Okay.
And also, so since if you take the overdrive voltage relation with the your current, if I pass the same current, your overdrive voltage will be like 1/4, because it's a square law equation, right? VOV square. Your current will be related to VOV square. So if I want to reduce the VOV, right, it should be 1/4. Like basically, I want 2 overdrives here. So my basic length should be increased by 4 times to match the same current. So this is the theoretical value. So practically we keep more than 4. So general value is 6, 8, 10, something like that. So I have used 6 here as a length. Okay.
Okay.
Yeah. So why 10 here? Because so I have stepped down the current already with respect to this. So I can use the 50% of the total width that is offered by this MOSFET. Okay, even you use full 19 micro also, this will not affect, because I already stepped down the current here.
Okay.
To the 50%. So it's a 100 micro here. So I use, you can say 12 here, right? 12 means here it is 24, 23. So it's already 50%. So I step down by half. So basically maximum current that it can flow in this branch is half of the tail current source, right? That's what I have used it here. This part is clear?
Yes.
Great. So now coming to this part. So I have to generate this now. Okay. So how much minimum voltage I want here? 1 overdrive and 2 overdrive and 1 VGS. Essentially 1 overdrive, 2 overdrive, 3 overdrive plus 1 VT. So how to do that? This will be giving one overdrive for me. This is second overdrive. This is third overdrive plus 1 VT will be this their connected configuration. So that's what I'm generating here. Simple. And why this is directly connected here? Because I don't want to extend this branches further. I'm just turning it off, closing this branch. If at all you want to have one more branch here, right, this no need to connect. You can just use it as a mirror and do it here, or you can use this as a mirror. It's basically after completing, you are writing something in your textbook or a notebook. So after completion of the sentence, you will give a full stop, right? This is kind of full stop here. I don't want to extend my biasing circuit further. So how will you give full stop? Just a direct connection. Okay. Any questions? So if I did not do direct connection, so this gate has to be driven by something else. If I connect it here, this will not work because the length is already 6 here. Okay. Then if here the length is 1, then again it will step down the current. And moreover, we already taken the current mirror here. So in the same branch, you cannot have the 2 current mirrors driving the 2 different currents. It should be single current driven by only 1 current mirror. Okay. That's why this direct connection will come here. Is that point clear or it's some confusion?
Yes, it's clear. The biasing is clear. So the MOSFET above M17, is it in region 1?
Yeah. This is in region 1. Yes, perfect. So essentially, so this we have used, or else you can delete also, like this is not needed, because this particular MOSFET will have enough, overdrive voltage here. You can see it here, right? So how much I want here? VGS is 876 millivolt. Plus, let's say VDS is around 400 here and 300 here, like 700 plus 800. So 1.5 volt minimum I want at this point. 1.5, 1.6 volt. If you see here itself is it's 1 volt, it is dropping at this point, and 700 at this, sorry, 500, around 600 at this point. So it's more than 1.6 I am getting here itself. So I have just kept this because just to have a little bit more margin here. So this is needed. Generally, this will always try to pull in this triode, but if you tweak further, definitely it will be also in the saturation region. So for that, we need to like tweak more and more. Basically, do more iteration, you will get into saturation. But as of now, it's not needed. But your point is right, so it should be in the saturation as well. It should be. Okay.
Okay.
So how can I make that in the saturation region? But you just tweak it, sir, to reduce the W2, let's say 0.5. So real to 0.5. Oh, this is not editable. Huh? It will work definitely. So you can just try tweaking it. Sorry, I was looking this. Now the VDS becomes 74. So anyway, so this will be fixed, but you can try. If you're not able to, I'll help you guys. But I don't want to like concentrate more on this and spend more time. Okay. We'll do for other analysis on the same Opamp. Okay. It will be fixed. It's very easy. Just try to tweak this branch, this MOSFET and this MOSFET. And it's not necessary you should fix it. So region 1 is also fine for me. But supposed to be region 2. Yeah. Any questions, guys? Okay. So now we'll proceed further and we'll do different analysis. That is pole zero analysis. Okay. Pole zero analysis, we will do it. You can see, right, how many poles and zeros here. I'm worried only with respect to this zero hertz this thing. So I'm least bothered about other high frequency portion zeros. I want only low frequency portion zeros. Essentially these two. See, you can see, right, there is only one dominating pole here, and there is one more dominating pole on zero at some frequency, but that is cancelled out. You can see, right, pole and zero are at the same location. This will cancel out. Only the mattering for me is this. Only this. This is a one pole. That pole is at some 1.9 kilohertz frequency. Okay. Any questions, guys? No questions? Okay. So pole zero is done. Then let's try to do some transient analysis also. Okay. Transient should be done on which circuit? Slew. Now we will see the result for this. Here again we will try to find out. You guys can make difference, right? You remember in the two-stage Opamp, this was slow, sluggish, and it was slowing very. It was very slow. Now you can see it is very fast. You can make that difference here. Okay. Now this with respect to 5%, if I take, it will be 2.357 something. 2.35. Yeah, let's check this. You can see it's just a 62 nanosecond. Before it was how much? It's 192 or 195 nanosecond, right? For two stage settling time. Correct, right, guys? Here the settling time also got reduced because it is a high gain amplifier. Along with that, it is one dominating pole system, because of which I'm getting very good phase margin. Okay. Okay. Now this is a settling time, and meanwhile we can also plot slew rate. This is a slew rate. Okay. If you consider that here, the positive slew rate is how much? 33. Negative is how much? 27. So basically we are getting overall average 33. 30 volt per microsecond. It's very fast, man. It's really very fast. Okay. So we saw slew rate, we saw settling time, DC analysis, AC analysis, in the and Topology analysis, and what else is pending? This is anyway, it's a transient analysis only. If we give that the sine wave, it will come as a sine wave. Okay. Now we'll go for other simulations. So any questions, guys? Just since we already covered this in the two-stage Opamp in detail, so I'm just moving fast. Okay, let me know if it's fast and like you want to have more discussion. Okay. Let's go to stability now. Okay, now for the stability, we will see how much it is. Hold on. So this is still pointing to storage stage open. Yes, then I have to close this and open the fix it here first. Yes, that's perfect. Why? Why this is not coming? I probe 0 and it is there, right? Okay. Hmm. There is something wrong here. It's not able to compute the simulation now. That's the problem. It is able to. What it is telling is the gain in dB is always less than 0 and loop is always stable. So no gain margin and phase margin is telling. Okay. Gain is always less than 0. How it is always less than 0? Oh, it should come something, some numbers. So
Hello.
yeah.
I have a small observation. Like the phase plot that we plotted here, that starts from I think 180 degree. Is that correct, or it should start from minus 180 degree at 0 hertz?
Oh, is it? Okay. It should
Can you
start.
just recheck
It should start from
recheck
0
the?
degree. Okay. Yeah. So what is this 2 it is coming? Correct. Uh-huh. It makes sense. Makes sense. I got it. Why? So what I will do is it's now starting from 0, right? See what happened is, so this is a single stage op amp, right? So the terminal, this terminal input terminals are like swapped. So I just kept same as that of 2 stage, but actually this is positive terminal, this is negative terminal, right? See, the names are ulta. This is negative, this is positive, it is telling. Okay, that's why by looking at the outside, right, I thought like I drawn with respect to the input, so it will come ulta like 180. It starts with 180. Okay, did you get?
Yes.
Yeah. Okay, that's fine. No problem. This is not an issue. Yes, and this could be the one reason. It's a good observation, by the way. So let's try to edit the symbol here itself. Uh, since that we are making it positive loop, that may have it should have effect also. Let's try to edit it. Why not? Okay, now this is perfect. Let's try to have this in the symbol as well. What we have used it here. Okay, this is Vn and Vnp, right? Now what here? Okay, now what I'll do is I'll go to the stability one. Okay, now I should have the stability stability be printed up. Yes, ma'am. Hey, Facebook is coming 165. Really? Okay. So come. How much did you get phase margin previously? Anyway, we are getting result, but it's fine. I mean, means we are on the track. But why it's coming 165, we need to check it here. Okay, it should be right. Yeah, it is 88 degree. It is coming here. But why it's coming double there? Mhm. Still, it is 88 degrees. Huh? So it's coming double there actually. In case of stability, it's coming double. Huh? So 2.9. You guys have any thought on this? Any one of you? Okay, let me get back to you on this. Why, what exactly happening here? Okay. Any questions over? This completes complete Opamp. Okay, Opamp theory plus lab. Okay, please do all these assessments that have given, writing the expressions, and by try to do these labs by today itself, so that tomorrow you will come with some doubts if you have any. Okay, both two-stage and cascode, and try to do after this, right? You have to do on your own this folded cascode. That is also important topology. It's just improved version of even derivation also. It's improved version of this gas telescope. Okay. Just take overdrive voltage of 200 milliwatt and just start deriving the W values and see simulation results in the lab. If you face anything, right, let me know. Okay. Now you got some, grip on the circuit design, right? Like how to design, how to start with the design. So what all parameters to tweak and what all the assumptions we should make, right? So everyone, I hope got this. If not, right, let me know. If you are stuck at somewhere.
Hello.
Yeah.
Sorry, I have a small question here. Like, when we designed the telescopic Opamp and we calculated the phase margin, we are seeing like a open loop phase margin somewhere around 87, 88, right? And in the stability analysis also, we are trying to match the phase margin in a closed loop system. So if we have multiple loops going on from output to input, suppose, so is there a possibility, depending on what kind of loop it is, suppose it's a positive feedback or it's a negative feedback, that can change the phase margin that we are seeing on the stability analysis? Is it correct to say that, right?
Yeah, so I'm not very confident to say yes. So let me get back to you on this. Okay. But it ideally should affect that, whatever you are telling. Okay.
Okay. Thank you.
Any questions, guys? No other questions? Okay, then you please work on these two labs. So on this stability thread, I'll get back to you maybe by tomorrow or maybe by next class. Okay, please remind me. Okay. No questions means we can conclude.
So sorry, the ADXL is still not running, so we will have to do the corners by ADL only, like selecting
Right.
single,
Right.
and then
Yes.
changing.
Yeah. So now, as of now, right, you can do like 3 simulations. One is like slow, typical, and fast. So all analysis you have to do three times in the ADL itself.
Okay, thank you.
Yeah. So better try to design it for slow corner. Okay. And fast. So typical anyway work we have seen right now. So I have done all the simulations for the typical. Now you can do slow and fast, 2 simulations. Okay, guys. Thank you so much. See you tomorrow, and we'll start with a new topic. So the next module. I hope I have shared this particular Opamp topic document to you guys, right? So please work on this. It's very important topic. So all the upcoming topics and projects depends on this particular module itself, Opamp. So Opamp in turn depends on diff amp and single stage. Okay. Yeah, work on it. Thank you so much, guys. See you tomorrow.
Thank you.
Bye bye.